So good morning, everybody. So today we're honored to have Dr. Keo Obishesan here. He's going to be talking with us on statistical modeling in R. So the agenda is going to be, we're having our participants in here already. So we'll be admitting others as they come in while the program is going on. So the agenda, we're going to introduce the organizers of the Abuja R user group. Then we introduce our speaker. Then we'll allow our speaker to talk with us for 1.5 hours. So if that's not enough, then we'll extend the time like 15-30 minutes, depending on his request. So then we'll have time for Q&A. So we'll ask questions. So if you have any questions, just let's kind of wait for our speaker to finish, or if you request that you can ask questions, then you can go ahead, we'll give the time there. So with that, we will start the program. So I'm going to introduce the organizers. We have Jude Fowowe, is a statistician based in Abuja here, unavoidably absent today. So I'm Biliki Sowumi Adenrito. I'm a business data analyst based in Abuja as well. We have Danladi, a medical doctor. Then we also have Abubakar Ibrahim, is also a statistician based in Abuja here. So we are all addicts of R. We love R, and we are using R in our different professions and fields of work. So we are really honored to have something in common with all of you. Thank you so much. So without wasting much of our time, I want to introduce our speaker. So our speaker today is Dr. Keo Obishesan. Currently, he is a senior lecturer in the Department of Statistics at the University of Ibadan. So that's University of Ibadan here in Nigeria. So he's the postgraduate coordinator 1. So Dr. Obishesan has taught statistics and mathematics at various institutions, including the Polytechnic of Ibadan, Ladoke Akintola University of Technology, Ogbomoso, the University of Melbourne, Australia, Clemson University, USA, University College London, and the newly established First Technical University Ibadan, where he went on sabbatical. So he's also a statistical consultant to the World Bank and the Federal Ministry of Water Resources. He is a member of the National Technical Committee on HIV/AIDS database. So at this junction, I would love to invite Dr. Obishesan to take the screen now and start the program. So you can share your screen.
Okay. Yes, thank you very much for that introduction and the opportunity that that the Abuja has provided. We don't have much time to waste. I just have to go straight into the discussion. You know, the title of today's presentation is on statistical modeling with R. If you remember when we discussed that title, I told you that it's very broad and so many things needs to be discussed. When you say statistical modeling, it's a very broad, very broad topic that a very brilliant statistician will want to run away from it, because when you say statistical modeling, it involves a lot of things. But in this presentation, what I will try to do, I will try to limit the kind of models I will discuss within the frame of time. In this presentation, I will do a bit of introduction, and I will do a bit of introduction, and then I will talk about statistical modeling with R, and then I will limit the modeling that I will discuss here to linear models and non-linear models. of course, when you look at the majority of those models that we normally use, they can be, most of the models can be categorized broadly into two groups, the linear models and the non-linear models. So, of course, those of us who have been familiar with R, you want to find out what kind of models are very common. So in this presentation, because I plan to give you the slides later on, I will use some library. Those of us who are familiar with R knows that library are groups of packages and programs that are, that have been written, that have been pre-written to assist you in the work. So there is a library called Equationmatic. There's another one, Tidyverse. That one is very common. Another one is GG45, and another one is KRET and MLBench. So these are the major packages that I'm going to be using. So when people talk about R, since 2010, when I came back from the University of London to University of Ibadan, I have been opportune to discuss, share, and teach R with so many people, even with the National Mathematical Center in Abuja. I know R is a programming language. It's free. All of us know that it's free. Although, if you need to learn R, you need some time. It requires some investment. Part of the investment includes time. So, of course, it is free. It is free, and it's an extensible environment for manipulating, plotting, and analyzing data. R has become very successful indeed because so many organizations now move into R. Recently, the IITA in Ibadan wants to move from Stata to R. They are not saying Stata is not good, though. Stata is very good, but there are some concerns in IITA now that the thousands of dollars that they normally spend every year to renew the license of Stata, some scientists at IITA are concerned that if they move their work away from Stata a little bit and then go into her, that they are going to save some money. So the world over, everybody is looking into her. Everybody wants to get into her. Now, hello.
Yeah, can you give us a full screen of your slides so that we can see it better?
Okay.
Thank you.
Can you see a full screen now? Do you have a better one now?
Yes, it's better, sir. It's better.
So it's a lingua franca. It's like R has grown to the extent that it's now like if you have a community that speak a particular language, if you're actually from that community, you should be able to speak that language. So for statisticians now today, I can boldly tell you that R has grown to a situation of what we call a lingua franca. It's now getting very close to say that if you're a statistician and you cannot use R, then there is something, then you are not complete. So there are so many books have been written in packages in R. It is increasingly used in many areas. So many areas of sciences now, from anatomy to zoology to biology. It's an A to Z thing. R has become an A to Z matter now. Then most of the time, most of the packages in R were developed by academics all over the world. It started at somewhere in very close in New Zealand, at a university there, in the Department of Statistics. So many universities across the world have people developing packages on a daily basis to solve one problem or the other with R. So right now we have Unix version, Linux uses it, Windows and Mac. So there is also a similar program called X+. X+ is not free, while R is free. For me, I always tell people I use R because of 5 to 6 reasons. Number one, R allows me to write my functions as against many existing program packages. So in R, I try it. It has trained me to write codes. I write codes. I write my codes myself. So I am in charge. So this is the difference between R and sometimes SPSS. So in SPSS, you have to go to a particular menu and click until you get your result. I know some people now say that in SPSS, there are also places to write programs, but majorly SPSS is point and click. So in this R, you just write your own code and you are in charge. Number two, those who like to use R, you must know what you are doing because it's not menu driven. There's no room for point and click analysis. For me, it's a great advantage. Number three, it allows me to learn and improve my programming skills. Number four, apart from being free, R allows publication quality graphics and original analysis. You see, many scientists come into R because when you draw when you need to do a graph, you see the quality of the graph, you see the legends, you see the axis labeling, you see everything very clear. Then on daily basis, new analyses that are being developed are included in R. So as we are talking today, a model that was difficult to program yesterday could have been written into a package by someone. And before you know it, it's going to be loaded on the R base, and then it's going to be available. So R has assisted we statisticians and majorly many scientists and engineers all over the world to solve so many problems that used to be very difficult. Then, most of the time, when anything you do in R, you see the results immediately. So every command immediately after the instruction, and there is no room for, and there is room for correction. Then there are apps available. So if you want to do something and then you want to, you want to be assisted, there's a lot of library for apps. Now, I think I need to mention something. In Unix or Linux, you start your R by typing R. And of course, in Windows, you only need to click on the icon. Most of our system here, I'm sure most of us use Windows. So when you click on the icon, you'll be able to see the R. Then, you start by typing instructions. You can get your R at www.cran.rproject.org. So it's everywhere. It's there. There's a lot of things that there are soft copies of textbooks on R on that website. It's been supported all over the world. There are versions for Unix, Linux, Windows, and Mac. R is free and is faster, although through professional training. Now, there is RSTUDIO now. When you say R, the last training I went to, somebody was asking me what's the difference between R and RSTUDIO. This setup aims to install both R and RSTUDIO. What you do is when you install R, you should install RSTUDIO. Then you can think of installing R as buying a car, and of installing R and RSTUDIO as buying a car with all the accessories for a better user experience. So if you install R, it's just like buying a car. When you buy a car, you have to be the one that be looking for all the accessories. But when you now install RSTUDIO will provide the accessories, the background or the environment on which your R will work. So, okay, so we have to differentiate between that. So R refers to a software environment that comes with a GUI. So many people call it GUI. That means graphical user interface. How GUI looks more similar to the old DOS console than to SPSS or Stata. RSTUDIO is an IDE, integrated development environment that makes R easier to use and is more similar to SPSS or Stata. It includes a code editor, debugging, and visualization tool. So please use it to obtain a nice R experience. So RSTUDIO, we make you to, you will want to continue using R if you use RSTUDIO. Now, how do we install R on Windows? The website I gave to you, the CRAN project website I gave you, if you get there, you will see those options. If you see my cursor, you see download R for Linux, download R for Mac, then download R for Windows. So all this, any of the program you have, R will work on it. So when you click on any of them, it immediately runs on your computer. So step 2, you run the installer. Default settings are fine, but there is something you must note. So many people they don't take note of this, because if you do not have admin rights on your laptop, for instance, if you borrow somebody's laptop and you don't have the administration rights, you have to request for assistance from the IT support. it is important that you also ask them to provide you for full permissions to use the R directives. Without the full permissions, you will not be able to install additional packages later. When I went for the last training with the National Mathematics Center in Abuja, there, so many of the participants did not, they got their laptop from their brothers and sisters and brought them in. So each time we wanted to install any package, they would say, sir, we cannot install our package. It's because you don't have the rights. You don't have the password, you cannot install the packages. Hello, can you hear me? Can you hear me?
Yes, sir, we're hearing you. Okay,
so now after downloading R, which is free from that website, I always advise my people to download RSTUDIO next, because I've just told you that installing R is just like buying a car. But by the time you install the RSTUDIO, they have to provide the accessories with which the car will work very fine. So RSTUDIO is going to provide the environment that makes the journey into R to be very interesting. So when you install the RSTUDIO, it also has so many options for so many programs. The window is there, the Mac is there, Ubuntu is there, and all of them are there. So you just click on it and then you download your version. Okay. When you run the RSTUDIO installer, after you have completed the R installation, you have to still be careful. If you do not have the admin rights on your laptop, you have to request from the IT support. Now, when you install the RSTUDIO, this is the menu that you are going to have. Can you all see this menu? Hello? Hello? Hello?
Yes, we can see your screen.
So this menu now, this is the environment where you write your code. This first environment is where you write your code. When you write your code here, then the description of all the objects on your system will be here. And then you have another menu that contains all the packages that are available for you, all the packages you are using for this particular assignment. So the difference between R and RSTUDIO has been clearly stated. For R, you don't have all this menu there. You have a particular menu. You are the one that can be creating those menus to do whatever you want to do. But for RSTUDIO, it comes with all the accessories with which you run your R. Now, I want to go into the topic proper, because all those things I just said are just mere introduction, and there's no way you want to do anything R without doing a bit of introduction into what R is and how it can be done, how it can be obtained, and how you can actually use it. The title that we have is Statistical Modeling with R. When we were discussing this title, I told the coordinator of the Abuja Hub that this title is very broad. It actually is something we can, it's a general topic that even if you ask me to deliver a 2-hour lecture every Saturday in the next 6 months, I cannot finish this title. So what I have decided to do is to get a limit of what can be done within the confines of this little period that I have. So today, I told you from the introduction that I will limit my statistical modeling in this case to linear model and non-linear model, because I believe very strongly that those two kinds of models can give us a tip of the iceberg of what we need to know for now. Okay, so what is introduction to statistical modeling with R? R can be used to perform a lot of modeling activities in science and engineering. However, in this presentation, I intend to limit myself to simple example, such as a way that so that participants may be able to work on their own. So the way this slide has been done is done in such a way that you could go away with it, and maybe after the trade, after this presentation, you can also carefully go to a quiet place and try to follow some of the instructions on the slides with R, and then see and try to get all the results that I'm going to be showing you very soon. Okay. I will discuss linear and nonlinear models with examples. In the first instance, I will restrict myself to simple models as discussed in Skladnowski 1998, Sieber and Witt 1987, Rees and Strebik 2008, and I will proceed into using the R language to fit a nonlinear model using a practical example. So, you know, I've told you that when you say statistical modeling, it's very broad, but I'm restricting myself to both linear and nonlinear model here. In fact, when you say linear models only, we can do a short course for 6 months for linear models. Talk less of linear, even if it's non-linear model, we can do another 6 months, a full semester course for non-linear models. So there are so many things involved. So here, I've only come here to do a little, description of what this is. Just a tip of the iceberg for statistical modeling. So linear models. Well, before I open the next slide, I just want to say something that I know that many participants that we have here are, I know we all come from various backgrounds. I know we come from various backgrounds, so I believe strongly that most of us have at least a middle-level manpower qualification, maybe something like maybe a secondary school qualification or a national diploma or a first degree with an HND. So I will try as much as possible to make the modeling aspect as easy as possible. Okay. How do I explain this? Linear models are those models that are linear in their parameters. For example, if you have a y, a y high is equal to alpha plus beta 1x1 plus beta 2x2 plus e high, or a particular error, or e. So now the idea behind this comes from the equation of a straight line that we normally write in secondary school, where you say y is equal to mx plus c. Remember, in secondary school, we used to write y is equal to mx plus c, where our m is the gradient, x, we say x is the horizontal axis, we say y is the vertical axis. Then we say c is a constant. If you remember, we say c is a constant. So in this linear regression model, this y is like the response variable. This y is the response variable. And this alpha is just like that c in our equation of a straight line in secondary school, like a constant. So this beta 1 is just like the slope. It's just like you build this beta like the slope. So this equation that I've written here has like beta 1, beta 2. It's as if the slope has been segmented into 2. So in statistics, we say alpha, beta 1, and beta 2 are parameters. We say they are parameters, where the E here represents the random error components of the thing, random error component. So this is a typical case of a multivariate linear regression model, because we have two variables here. You have y as the response variable, you have x1 as the independent variable, you have x2 as another independent variable. We can, for the purpose of most of us who are not mathematically inclined, an example of this is to probably say that you have income and expenditure. When you say income and expenditure, you want your income to depend on your expenditure. What I'm trying to say is that if I'm collecting 30,000 naira as my salary, and then you discover that my expenditure per month is going to like 1 million. So in that case, you want to think that I have other sources of income. That's why, so you expect my expenditure to depend on my income. So expenditure, why can stand for expenditure, where the x1 can be income. So my expenditure depends on my income. My expenditure depends on my income. Then if I have other sources of income, I can say my expenditure y depends on income, my salary. Maybe x1 is my salary. Then x2 is other sources. Hello? Can you hear me? Can you hear me? Can you hear me?
Yes, sir. We can hear you loud and clear.
So I want you to view this equation I've written as a particular expenditure, y as expenditure, x1 as my salary, x2 as other sources. So it means that my expenditure y depends on my salary, and other sources. So this equation I've written, in statistics and mathematics, we do what we call numerical representation. We use these equations to represent reality. Models are abstractions of reality. We use equations to represent reality. So this kind of equation can be used to explain a lot of things. It can be used to forecast my salary in the next 20 years. In fact, I can have an estimate of what I will collect throughout my retirement. So these kind of models are very important. Now, again, as I have decided to, I've played down the equations. Each time I talk to a large audience like this, I always want to be very careful and I want to dwell more on the application. However, I cannot do some of this modeling without equations. So that's why I'm spending time trying to explain that, sometimes you would have to find a way of explaining it to each other. Suppose we have a univariate response Y being related to a possibly multivariate predictor variable X through a function F. The function F is not completely known, but it is known up to a set of P unknown parameters. Like I said the other time, that the set of parameters can be represented by a beta. For clarity, the relationship between the predictor and the response can be formulated as a Y is equal to a function of X that has a beta in it. Y is equal to F of X beta. Y is equal to F of X beta. Now, I was explaining income and expenditure. How do we now use R? How do we use R to find answers to questions that we have? Let me go back a bit. Remember this model again. This model is using this model. I'm using this model to explain the relationship, thinking that my Y is my expenditure and that X1 is my salary and that X2 is other sources. Suppose I published a book. So I will be receiving money, income from my book, and then I will be receiving my salary, which is usually fixed. So now, how do we use R? How do we use R to explain this? You may need to read the F files on the commands. There is a command in R called LM. LM. LM means linear models. And of course, what we call stepwise regression. Stepwise regression. So now for the purpose of this presentation, for you to be able to learn about how to use linear model how to use linear model with R, how do you do it? You can just type FLM on the R prompt. If you type FLM on the R prompt, or you can also type a question mark before the LM. The moment you hit the enter key, you will see a lot of explanations in it. A lot of explanations. That was why I said R requires some investment. Part of that investment is your time. If you want to enjoy the quality of what R can do, you need a bit of time to actually sit down and study. Now, another one that you need to learn is what we call stepwise regression. Those of us who are statisticians know what I'm talking about. When you say stepwise regression, you are saying that since I'm talking about my salary and others as the variables there. So which one of the two variables will determine my expenditure? Is it majorly my salary or the others? Is it majorly my salary or the others? It's possible. I can compare two of them. Using regression models, using statistical models, I can be able to know which one has a very strong influence. Out of X1 and X2, we can determine which one is strong, which one is weak, which one is influential, which one is not influential. And that is what leads to the issue of stepwise regression, where you can regress. First of all, regress X1 and see the effect. Later, you regress X2 and see the effect. So all those processes that we normally do, that we follow linearly, normally, can be done computationally using R. But I always advise people, understand what the computer is doing. That's why I always use my hand to first of all write a draft of the model, then I imagine what the model will do, then that is when you can appreciate what the computer is doing. Of course, what you find on the computer is also written, it's written for the computer in terms of programs. Okay. Now, if you have y, x1, x2, and you need to fit a multiple regression, the model, this model, can you hear me? Hello? Hello? Hello?
Yes,
hello?
we can hear you, sir. Thank you so much. We can hear you.
So look at the x1 variable in R, inside R, you can create the variable yourself. We are starting with this version because this is the easiest way to do it. If you create a particular data yourself, you understand how to create the independent variable, or even the response variable can be created in R. I don't know if I'm right to say that there's nothing you cannot do with R. That's why I stayed with R for a very long time. R has come to stay, and most of what we want to do, we are able to do them. If there's a problem today in R, before you know it, before the end of that week, somebody somewhere will write a program that can solve your problem. More so, so you can also get support from many places. I'm creating X1. This X1 from this variable. Can you see this X1? I'm creating it. I am creating X1. I'm asking her, I'm saying, please help me to generate help me to generate 25 numbers that ranges between 1 and 10. Hello, can you hear me? Can you hear me? Hello?
Yes, we are able to hear you. We can hear you, sir.
Okay, so the first variable, the one that talks about my salary, I said y is my expenditure, and I said that x1 is my salary, and that x2 can be others. So if I ask R to simulate 25 numbers from that ranges between 1 and 10 for me, so my x1 is like, it's a sequence that ranges between 1 and 10, but there are 25 in number. That's the meaning of this statement in R. While we were preparing this, I would have commented it here for you to see. So I will have commented it and put a heart sign for the comment. But that's all right. X2 is saying, okay, I'm asking her to simulate 25 numbers randomly from the uniform distribution. All of us who are statisticians and people who are not statisticians that are here, you know that you can also generate, you can simulate values. So for the others, for this X2, I'm asking her to randomly simulate 25 numbers from uniform distribution that has parameters 3 and 7. Those of us who are statisticians and those who are not statisticians, we know that there is what we call A and B in uniform distribution. In this case, A is 3 and B is 7. Hello? Hello? Hello?
Hi. Hi. Yes, I can hear you, sir.
Oh, yes. Oh, yes. So the response variable can also be written as a function as you like. So I am doing hypothetical data generation with R. I'm bringing in my data. I'm bringing in my own data using what you know already. So that's what I've done. I'm creating the response variable also, because before I can use R for this linear model, for this simple linear regression or multiple linear regression, I must create the variables. I must create the Y, the response variable that represents my expenditure. I must create X1 that represents my salary. I must also create X2. Don't forget that I made an explanation that you should build the response variable as something that depends on the other. The response variable, like Y, is my expenditure. That is what I spent before from day one of the month to the end. And of course, X1 is my salary. So what I'm spending, what I spend to take care of my family should depend on what I earn. So a variable Y represents what I spent, my expenditure. X1 represents my salary. X2 represents other sources. And I explained to you, if I collect 30,000 naira per month, and you see me spending 1 million naira per month, so you want to think that something's fishy. Okay, His salary is 30,000. He's riding a Rolls Royce. He's riding a Mercedes Benz. Where is he getting money? So it's possible. It's possible. I can have a hot selling book that I've written, and that hot selling book I can be getting income from there. So how do we model this situation? Can we use statistical models to get that using her? So the answer is yes. So I am hypothetically producing X1. The statement to produce X1, I want 25 numbers. I want 25 numbers. I want them to range between 1 and 10. For X2, I'm simulating from the uniform distribution randomly, 25 of them. I want the parameters of the uniform distribution to be 3 and 6. You can change it to anything you want, but just listen to this one. Don't touch this one for now. By the time you understand this, then you can change that. Then for my response variable, I say I want 4 plus 2 multiplied by X1 plus 7X2 plus 25 numbers randomly simulated from the normal distribution, you know, but the mean of the normal distribution is 0 and the variance is 1. Hello, can you hear me? Hello, can you hear me?
Yes, we're still with you, sir.
I like to talk like that so that so I won't lose you. So I don't like to just be talking without carrying my people along. All right.
Thank you.
All right. So now, after the creation of the variables, I've created Y, I've created X1, I've created X2. So how did I create Y? I created Y using this equation myself. What is 4? We know 4 plus 2X1, already we have X1, plus 7X2, we already have X2, plus R norm 25,01. This is the way to simulate 25 numbers from normal distribution using R. This one is the way to simulate 25 numbers from a uniform distribution using R. And this one is the way to simulate 25 numbers, you know, that range between 1 and 10. You see, there's hardly anything you cannot do with R. I repeat it. I repeat it. You know, I repeat it. Okay. Now, now in R, I can decide. Those of us who did basic programming languages in year 1 of our degree courses, you know, those of us who did Fortran and basic programming those days, you can remember this. You can name this as model 1 or mode 1. Don't forget, I said there's an instruction called LM, linear model, LM in R, and that instruction is saying Y la X1 plus X2. This statement you have here, is actually representing the whole of this, Hello, can you hear me? Can you hear me?
Yes, sir.
Yes, the statement I have here represents what I have here. If not the time, I will have numbered the equation. I apologize for that. I will have numbered the equation to make it easily referenced. But now, this statement here, the equation that I was trying to explain with the income and expenditure, can be written in R using this. You can see, can be written in R using this this one. Don't forget, I have done something here that you should think about. I said my data. Then I said table Y is equal to Y. X1 is equal to X1. X2 is equal to X2. So I have created a kind of table that will combine all those three data that I created, hypothetical data that I created. So inside the linear model statement in R, I've written Y la X1 plus X2, comma, data is equal to my data. That this my data combines all the three. Of course, the model is already here. The Y is here, X1 is here, X2 is here. Data is equal to my data. Then what is there any omission? Is there any omission? Is there any not availability action? You know, this response is saying not availability obeyed. So there is no, all of them are 25 values. So this statement is just there to say that all the information. Don't omit anything. Just run my regression for me. What is the regression I want to run? This statement is what I'm running. Can you see my cursor? Hello, guys. Can you see what I'm? Can you see my equation? Can you see it? Hello?
Yes, sir.
Yes. So I want to run that equation using the data I have provided. The instruction to do that in R is this, and I am storing the result in mode 1. I'm storing the result in mode 1. Let's go to the next slide. Look at the result. Look at the result of mode 1. Look at the result. Can you all see that? Hello? Hello?
Well, actually with you, sir. We are with you.
Okay. So look at the call now. The model that I told you about is here. The instruction you wrote is here. Then the residuals are here. Then, of course, the coefficient, the alpha and beta. Maybe I should go back there. Let me go back there. Don't forget this equation. I told you the parameters that we are running, that we want to know is alpha, beta 1, and beta 2. Don't forget it. Alpha, beta 1, and beta 2. Hello? Hello?
Yes,
Can you
sir.
hear me?
We are really enjoying you. We are enjoying you.
Yes.
Yeah, and I'm also following up with the chat box.
All right.
So I'm yeah. So
yeah.
well,
So
with
I'm
you,
actually interested in estimating alpha, beta 1, beta 2. And there's another parameter in statistics, the variance of this error term. The variance of this error term. So as you are looking at this model, that's why I said if I'm talking to, there's a way I talk to statisticians, there's a way I talk to mathematicians, and there's a way I talk to the general people. We don't all have the same background. That's why I'm emphasizing this. If this is a statistical class, I will have gone beyond this level. I'm going back to this model so that I can explain again. This alpha is a parameter. Beta 1 is a parameter. Beta 2 is a parameter. There's another parameter, the variance of this error term. You know, the theory behind that is not our business in this presentation. That's not our business for now. I just want to explain that. Now look at the result that we ran. Look at the results. Look at the results. This result that you see here, it's those of us who are used to SPSS in those days, know that the result from SPSS looks something like this. The intercept has been estimated as 5.255. That intercept is alpha. We have estimated, we have used R to estimate alpha. I want to go back to the this alpha has been estimated as 5.255. Hello, this alpha has been estimated as 5.255. .899, and of course, beta 2 is 6.8694. 6.8694. So, for your information, the theoretical background that provides that one is what we call the method of least squares. That method of least squares involves some equations, so I've kept that away. I don't want to scare you. You are all my friends. I don't want to scare you. But there's nothing really difficult in doing that. But I've kept the equations away, but I am interested in showing you how we have to do linear models with R. Okay. Now, to each of the parameters, there is a standard error that must be attached. The standard error that is attached to the intercept is 0.84706. The one attached to beta 1 is 0.06613. The one attached to beta 2, 0.15541. Then those of us who have done a bit of statistics at our undergraduate level, you know what we call the T value, the test statistic that will help you to take a decision on your hypothesis, if you remember. Now, what we do these days, we use what we call the p-value. The p-value, the one I'm running, the one, look at my cursor. All these guys are the p-values. These are the p-values. These p-values will give you an idea of how significant, if they are significant or not. Of course, if you are testing at 0.05%, you can see that these are 3.03 times 10 raised to power minus 6. The raised to power minus 16, raised to power minus 16. So these guys are very, very, very small. They are not likely going to be more than 0.05. If they are more than 0.5, they would not be significant. You understand? So now the residual standard error. I said I told you that there should be a variance for the error sign. So it's also estimated. Residual standard error is 0.8811, and the multiple R squared is 0.9934. Remember the multiple coefficient of variation. This one, you only need to multiply this value by 100%. This is 99%. It means the total variation in Y has been explained by the X's. The meaning of this is that this is your model. You are saying that in 99% of the cases, the total variation in my expenditure has been explained by my salary and the other income I receive. Hello, can you hear me? Can you hear me? Hello.
Okay, yes, sir. And now I think our audience will know that we're actually in a class with a professor. So yeah. we're surely with you, sir.
Yes.
We are with you.
All right. So now that is the typical result of a multiple linear regression for a statistical model for a multiple linear regression using R. You can use theta for it. You can use SPSS for it. So many languages can be used for it, and then you find all these similar results. You just have to be very careful in interpretation. Now, there is what we call diagnostics. How do I check that my model makes sense? Am I not just waking up one day and then just feeding models? Am I not supposed to just to check if what I've fitted is very correct? So in R, these 4 plots are embedded in R. They are embedded in R, for you to be able to see whether what you have fitted makes sense. Like I've told you that 95% of the total variation, 99% of the total variation in Y has been explained by the X's. 99% of the total variation in my expenditure has been explained by my salary and the others. That makes a lot of sense to me. So these are residual. This one is residual versus fitted. Once you look at this kind of graphs, and then you look at this one, look at the points. All these points are very close to the line. It's also an indication of the fair plots. And of course, further discussions on diagnostic plots, can also take several hours. Okay. All right. Now this is the diagnostic plots. Then we want to go to the next, to move into the next thing. Now, another way to do linear regression is as follows. Remember that I've created X1 and X2. I can also do linear regression like I've done here. I can fix X and then Y. Look at that same statement I wrote before. I can do it like this also. So R is very flexible. It gives you opportunity to get. You can see that these are all results. This same result I got before is what I have here. So it's just the same. It's just the same thing that we just did in another way. Okay, now I was trying to make a statement the other time that if you need to find out, is it my salary or the other variable that is responsible for my extravagant life? I earn 30,000 naira every month, but I spend 1 million. So if I fix a model that says, okay, he collects very few money every month, but he raises money from his book that he has published. And a model has explained that. Now, can we find out in particular to what extent, how much, to what degree, to what significance the particular variable has helped? Can we know how powerful is the salary? We can discover the power of that salary, how significant it is. Or of course, before you do the regression, you already know that 30,000 naira is too small, and then spending 1 million means that there is a 970,000 naira others, and that comes from other sources. So I can actually know the power of each of the variables. I can know the one that is very weak. I can know the one that is very strong, that is expected to contribute significantly into my extravagant life on my expenditure. Okay. How to do this? We call something forward regression and backward regression, and then both. So the idea of forward is, okay, suppose I have created Y and I've created X1, and if I don't have X2, they just see me that I'm spending a lot of money and I earn only 30,000 naira. Forward regression is also a kind of stepwise regression. Requires me to say, okay, let's add another variable. Suppose we had another variable. Suppose instead of saying others, if I say my salary and then a part-time teaching in another university. Suppose I teach in another university. If I teach in another university with my university here, I can earn income from both universities. So if I teach in 2 other universities in addition to my university, making 3 universities, I can also earn income from them. So I can begin to add new variables to explain my expenditure, and I can remove variables to also find out what is happening to a particular weak variable or strong one that will eventually be significant or not significant, that may be influential or not influential. So the idea behind forward and backward is the ambition to add more variables to explain my expenditure, or the ambition to remove some existing variables in order to explain my expenditure. So there is a package in R that can handle that efficiently. Of course, in this way, I can say, suppose I have linear model Y x1 plus x2. Data is the same data we have created. For the forward regression, you just write step. Then out is this linear model, this model. So if it's forward, it's going to, the way it's going to do, it's going to add the variable. So it will first of all run x1 with y, and it will later run x2 with y. For backward, it will run xy plus x2, and later it will remove x2. It will remove one of the variables, and then you have the result there. There is a lot of theoretical justification for forward and backward regression. It's very, very interesting. Okay, this is the result of the first one that has to do with the forward regression. So the forward regression, we have all the x1 and x2. The results are here. The results are here. Now, the next thing I'd like to talk about has to do with nonlinearity. Before I go to nonlinearity, let me go back to that equation that started the work. Let me go back to that equation. Yes, look at this equation. This equation again. You can see that there is a y and there is an alpha. It does not have any power. This is a beta, no power. I mean, it has a power of 1, rather, power of 1. This is a beta 2 with power of 1. So there is no quadratic expression here. And then the linearity is actually linear directly in parameters. The way they are, they are additive and they are linear directly linear. Okay. Now for nonlinear models, what am I supposed to do? Now, nonlinear models are those models that are nonlinear in their parameters. For example, we have what we call the logistic growth curve for sigmoidal relationship. Look at this relationship. Look at the way the relationship is. There is a yi is equal to a gamma e raised to the power alpha plus beta xi divided by 1 plus e raised to the power alpha plus beta xi plus ei. You know, this expression is actually non-linear in the parameters because this alpha is a parameter on its own. I mean, this gamma is a parameter. This alpha is also a parameter. This beta is also a parameter. The only way you can linearize this kind of an equation is to take the logarithm of both sides of this equation. I've avoided all those mathematical things because I believe I'm talking to a very wide audience, and I'm of the opinion that I know there's a way you give somebody a bitter pill to swallow, and that, I mean, when you smile and give me a bitter pill to swallow, I will swallow it. Before I know it's bitter, it will have been in my stomach that day. So this kind of a model can be logarithmized. I can take the logarithm of both sides and then linearize this one and then proceed as usual. Now, there's another kind of nonlinear model, the mystery equation for general asymptotic relationship. Yj is equal to alpha minus beta e raised to the power minus gamma xj plus ej. So this kind of equation is also a nonlinear equation, and of course, we can also linearize it. Actually, there are two types of linear models. I mean, of nonlinear model. There is directly linearizable nonlinear model. Those ones you can just introduce logarithm and linearize it. But there are some other groups called intrinsically nonlinear model. Those ones, even if you put introduce logarithm, you will not be able to linearize them. You will not be able to linearize them. This due to complex relationships in our world now, the COVID-19 situations that has taken over the whole world, that is disturbing the whole world now, you know, this kind of situation can hardly be linearized. The equations to model such effects, I mean, they are non-linear models actually. Hardly can you, because of complexities in the world all over now, you hardly can model complex situations in linear model. So most complex situations that are continuous now, that are all over the world now, are usually non-linear models. That's for another day's discussion. So application, non-linear model can be seen in many applied sciences, for example, in biology, physics, engineering, medicine, and pharmacology. You know, those of us that are into neural network models now, most of the neural network equations are non-linear models. Most of them are non-linear models. And of course, how do you explain a linear situation in a very complex world? Now, there's this particular group of models called generalized linear models. They are now like when you say generalized linear model, they are, you know, it encompasses, you know, most of this linear model and non-linear model, and of course there is this group of exponential family that, you know, you want them to emanate from the exponential family. But again, I have pruned down the equations. I don't want to scare you with equations, and when I am talking to a general audience, I don't bombard my slides with equations. I try my best to explain to the barest level. Okay, generalized linear models calculate non-linear regression when the variance in sample data is not constant or when errors are not normally distributed. So a generalized linear model commonly applies to the following types of regression. When count data is expressed as proportion, for example, those are logistic regression. Those logistic regression, we can do another 6 months data presentation or lecture presentation for logistic regression alone. So, you know, that was why at the beginning I said statistical model is a very broad topic and that we can only do a tip of the iceberg. You know, count data is not expressed as proportions, e.g. log linear models of count or of count. Then we have binary responses variables. If we have a yes or no thing, that's logistic regression. You know, data is showing a constant coefficient variation, time data with gamma errors. So in statistics, logistic regression is one of the most commonly used forms of nonlinear regression. Of course, it involves a lot of iteration, and the iteration has a theoretical background that we can prove, but not here. I mean, we don't go into that. We want applications and the usefulness of the models here. So in statistics, logistic regression is one of the most commonly used forms of nonlinear regression. It is used to estimate the probability of an event based on one or more independent variables. Logistic regression identifies the relationship between the enumerated variable and independent variables using the probability theory. Logistic regression models are generally used in cases when the rate of growth does not remain constant over a period of time. For example, when a new technology is introduced in the market, firstly, its demand increases at a faster rate, but then gradually slows down. Look at all the vaccines by the pharmaceutical world now on COVID-19. Most companies have used different levels of technology to produce their own. Logistic regression can be helpful in modeling those situations. A variable is said to be enumerated if it can possess only one value from a given set of values. Now, there are many other types. The multivariate logistic regression is there. This multivariate logistic regression includes more than one independent variable. I've been doing just only one Y. So when you have Y1, Y2, or Y1, Y2, Y3, you can think of multivariate logistic regression. It's usually used in the fields of medical and social science. It can be used to model COVID-19 situation that we have. We now have variants of COVID-19. The original one that blew the whole world, came December 2019, and then the whole of 2020 we were in the middle of it. Now now it's been said that we have different variants of it now. They said there are various types of COVID-19 now all over the world. Now, it is also used to make electoral assumptions, such as the percentage of voting in a particular area, the ratio of voters in terms of sex, age, annual income, and residential location, and the chances of a particular candidate to win or lose from that area. This analysis helps to predict the level of the failure or success of a proposed system, product, or process. Then we also have what we call multinomial logistic regression. This one, set of possible values are more than 2, and they are used to estimate the value of an enumerated variable when the value of the variable depends on the value of 2 or more variables. So, what are the logistic regression? Of course, in R, to define the logistic regression in R, we use the logit function. The logit function. This logit function in R. Logit function in R describe our logistic regression. So the implication is that the logit of x is logarithm of x divided by 1 minus x. So now, suppose P of x represents the probability of the occurrence of an event, such as diabetics, and on the basis of an independent variable, such as age of a person, the probability Px will be given as follows. So when you have this exponential function, you see that the probability of x is e raised to power beta naught plus beta 1 x1 divided by 1 plus e raised to power beta naught plus beta 1 x1. Actually, this is an exponential, and these are on the top. They are powers, but we can write them like this. So of course, beta is a regression coefficient, of course. So on taking the logit of the above equation, we get logit P of x is logarithm of 1 over 1 minus px. And of course, on solving the above equation, we get the logit of px, which is the simple linear model. This beta naught plus beta 1. Those of us who can recognize this, you will remember that this is the same simple linear regression that we know. The logistic function that is represented by an S-shaped curve is shown as the sigmoid function. Now, what is the post-logistic regression implementation? After developing a logistic regression model, you have to check its accuracy for prediction. adequacy checking techniques are explained. Of course, like the diagnostic graph that we saw the last time, logistic regression also has similar things. So there is this what we call residual deviance. When you have high residual deviance, it refers to insufficient logistic regression model. The ideal value of residual variance logistic regression model is 0. And of course, there's what we call parsimony. Logistic regression model with less number of explanatory variables are more reliable than models with a large number of explanatory variables and can be more useful. So on this parsimony thing, when you have many independent variables, of course, in that case, you are going to have many parameters. There's also what we call over-parameterization, which is also a function of parsimony. So you want to avoid many variables as much as possible. Then there's what we call classification accuracy. It refers to the process of setting the threshold probability for a response variable on the basis of explanatory variables. It helps to interpret the result of a logistic regression model easily. And then there is this prediction accuracy. To check the accuracy of predictions for the logistic regression model, cross-validation is used, which is repeated several times to improve the prediction accuracy of the logistic regression model. Okay, now we can try an example, because in statistics it's always very good to try, with all these explanations, you want to appreciate the work more when you get some data at hand, and then you try to fit the models and then see, how to appreciate some of the results. In this section, we will build our logistic regression model using the breast cancer data set that is available by default in R. There is this data inside R. So when the data is inside R, then you don't have any problem. Once you install R and you have internet, you have access to that data. Okay. So hello, can you hear me? Oh, I hope I've not lost anybody. Can you hear me?
We are still with you, sir.
Okay, so we will start by importing the data and displaying the information related to it with the GLMS. Now, look at this instruction here. This instruction will give you the breast cancer data inside R. That data is stored inside the package called ML bench. So this breast cancer data inside R has been stored inside a package called ML bench. Of course, putting that together, by the time you hit the enter key, this is the breast cancer data inside R. This is the breast cancer data inside R. Now, how do we do what we call data prepping? Data prepping now, people who do a lot of machine learning today know that statistics has gone beyond the ordinary. We now do a lot of work in, there's this big data technology thing that we talk about now inside machine learning. And of course, what we do today now is to group the data into two sets. So we split your data into training and test sets. So there's a training set, there's a test part. With the training set holding 70% of the data, and the test set comprising of the remaining, that's 30%. So the code to do that is to, of course, to store the data in an object called b_cancer. That is a cancer data. And of course, set.seed is just a statement. Those of us who are used to simulation and a lot of bootstrapping, a lot of computationally intensive methods, that set.seed, you can put anything to sometimes to set it, your seed. Yeah, I'm using 100 as my seed. Set.seed. If you want to begin a kind of work like that, you can set reasonable number. Now, the training part, we said it should be 70%, and that's why you have P of 0.7 here. P of 0.7. P of 0.7. By the time you give that, you pass that instruction of train _ratio into R for the beta, the cancer data. Then, of course, the test part is just saying training underscore ratio minus training underscore ratio is the remaining 30%. So you don't actually need the 0.7. So R understands how to do that. All right. Now implementing our logistic regression function using the function GLM and specifying the attributes family as binomial, we obtain model underscore GLM class 1 run on cell.shape. Class 1 run on cell.shape. Family is binomial. Data is train underscore data. So this train underscore data that we are working on, we want to fit a generalized linear model to data, to that cancer data. This is the result. This is the result of fitting a generalized linear model into the cancer data that is inside R. So look at this now. We have estimate of so many parameters. Look at the estimate. This is the intercept 4.78. The first parameter is 31.28, minus 6.24, 11.17, minus 0.03, 2.00, minus 13.34, minus 8.93, 2.38, 9.10. Then each of them has a standard error attached, like we did in the simple linear regression. I mean, the multiple linear regression that we ran. And of course, that's what we call deviance. Deviance, the dispersion from the real, moving away from the real variance. Deviance, 6.12, and the residual deviance is 139.75. There's what we call Fisher scoring iterations. That Fisher scoring iteration is the number of times the iteration is done. Now, when I started talking about linear model, I told you that it's a very complex thing that we can only discuss a part of it. We can do prediction with R. We can do prediction with linear model. We can do prediction with multiple linear regression. We can do prediction inside, using generalized linear model. So if we want to do prediction using our cancer data here is predict_GLM, predicts object is equal to model underscore GLM. So if you pass this instruction to R, you can have some prediction about R, of the cancer data. Look at this. Look at this. We can also generate the confusion matrix. We can generate the confusion matrix, and that confusion matrix is also useful for so many things. Ladies and gentlemen, as I've told you, a topic like this is very broad, and it's not something we can just finish in one class like that. But I just think I've reached a convenient point to stop for now. So thank you very much.
Thank you so much, sir.
Yeah.
Okay. I think now I'll hand over to Abubakar, who is going to share his slide.
Hello.
Okay. I think Abubakar.
Yes, thank you very much. Thank you very much, sir. Yes,
yeah.
Yes, Bilkis, I'm on.
Yeah.
Thank you very much, sir, for the wonderful and running us through R. And I believe many of us have seen it. And when you talk about linear, non-linear model, and the most interesting part is that most of people who have background in statistics have been hearing about. Can you hear me all?
Yes, I can hear you. I can hear you.
Yeah. So the most interesting part for me is when you start talking about machine learning, how big data, because in school, we are dealing with samples during our undergraduate and at the postgraduate level, we're always dealing with samples. But the coming up of big data now, where that is where R, I think, fits in because R can handle complex data.
Yeah.
Yes. Yes, sir. Without wasting much time, please, can we have questions from participants? Questions, please. Questions? Questions?
Okay, sorry, Abubakar. I think
Yes.
some people are raising up their hand. You can unmute yourselves now. I've enabled that.
Yes.
You can unmute yourselves.
Okay.
So
Thank you very much.
Maybe you have to watch.
Yes. Please.
Hello.
Hello.
Yes,
I'm here.
I can hear you.
I'm
Yes,
here.
thank you. Thank you very much, Doctor. My name is Joshua from TAG, Nigeria, and I want to commend you for this great job you've done, sir. More grace. Now, my question is just very simple. As to the code you use for your logistic regression, the place where you specified the family as binomial.
Yeah.
Is it possible? I used to see some kind of functions, codes where they also specify link. Could we have other options aside binomial? Like with
Yes.
that link function.
Yeah.
Thank you very much. And again, can we also have like what function can we use in getting some visualize some diagnostic plots for logistic regression?
Yes, excellent question. I love that question. The reason why we have binomial options there is because if you there is only, I'm trying to be clear, I was trying to be careful not to confuse you. I want to convince you. You know, when you talk about binomial situation, remember that in our theory, we will say Bernoulli contains two responses. We will say yes or no. Is it that a floor is cracked or not? You say is it that somebody is alive or dead? So any experiment that has to do with two results is the Bernoulli experiment, if you remember. So
yes,
for a binomial situation, once you repeat a Bernoulli experiment more than once, you have a binomial experiment. So it is because of that success and failure that leads us into the logistic distribution to get a binomial version. Actually, to answer your question directly, there is log link, there is normal, there is Poisson distribution. Other than the link functions can be so many distributions. It's not only binomial. To answer you correctly. So because it's because I was avoiding the theory. I don't want, I know many people have phobia for seeing so many terrible equations on the screen. That's why I put them down. There are many versions of link functions. Thank you very much.
Thank you, sir.
Yes.
Hello.
Next question.
Hello.
Yeah. Yes,
can
I can say Sherifat. Yeah, Sherifat, you can go on.
All right, thank you. Because my system is almost, I just want to thank the organizer for this session. In fact, I really enjoyed it.
Thank you, welcome.
And we don't know whether we can have access to the material. So that's my
why
question.
not? You can have access. Yeah, you can have access.
Will
We'll
be
send it.
I will release material immediately. It will be shared.
All right, thank you very much. Yes. That's actually my question. Thank you, Abuja, and the doctor, our able doctor from UI. Thank you, sir.
You're welcome.
Thank you.
Hello.
Hello. Yes.
Hello. Go on. Yeah. Samuel. Is it Samuel?
Hello.
Yeah. Go on. Balogun. Go on.
Balogun Lukman. All right. Thank you very much. Thank you very much, sir. I want to thank the presenter for the good work that he has been presenting all this while. My own question goes thus. I want to know the most preferred matrix for classification model. You know, there are some of the people, they make use of precision and some make use of F1, but as a student of knowledge, an undergraduate student that is looking for looking for knowledge of machine learning and all this thing here and there, we want to know which of those metrics is the most preferred for classification model, sir.
Okay. Are you referring to the matrices, the matrix?
The matrix, like F1, the precision, accuracy, confusion matrix, all those, I mean, adjusted R square, F1 that we use for precision.
The way you said it, the way you said it, I think you should have said maybe
Matrix.
model diagnostics, model diagnostic function.
Okay.
Model diagnostic.
All right, sir.
All right,
All right,
that's I love that question. Let me confess to you, I love that question. And I will answer your question from the commonest thing. Remember that in our model, you know, there is this E part that we normally write to represent error. Do you remember it?
Yes, sir. Yes, sir.
That E part, the difference between mathematics and statistics, that is the difference between mathematical model and statistical model. Remember, I told you that the equation of a straight line is y is equal to ms plus c. That's what I did in secondary school. Can you remember y is equal to ms plus c in secondary school? Can you remember it?
Yes, sir.
If you can remember it, in the university, instead of writing y is equal to mx plus c, you will now write y is equal to mx plus c plus ei. So the difference between statistics and mathematics is that in statistics, we introduce a random component to that equation of a straight line. So the moment you do that, don't forget that the theory to get the estimate of the parameters alpha and beta is to do what we call least square, least, L-E-A-S-T, least square method.
Right,
so that list comes from the fact that we want that thing to be very small. So least means the minimum error. So in other words, we are telling ourselves that we want to fit a linear model or a statistical model in as much as the fact that the error that we want to make or that the mistakes in the setup of the equation is as small as possible. So the fact that least square method is used to find the alpha and beta means that we must make the error sum of square very small. So that's why in statistics you say residual sum of square. So if you pick three models, my dear brother, you pick the one that has the minimum residual sum of square, meaning that you want the error or the mistake of that model to be as small as possible. So if you pick three models and the first one has 0.2, the second one 0.3, the third one has 0.4 as residual sum of square. Which one is the best model, my brother? I'm asking you.
It should be the one with the least error.
Yes, the one with the smallest residual sum of square. So now,
yes, sir.
Like you have said, the residual sum of square, as small as it is, the one that has the smallest one is it refers to the best model. Now, if I take that residual sum of square, it's also a function of the variance. You will see that if you have estimators that are many, you take the model or the estimator that has the minimum variance. Hello?
Yes, sir.
So you take the one that has the minimum variance. So if I have several models or several estimators, I will take the estimator that has the minimum variance. I will take a regression model that has the minimum residual sum of square. You know, so when people now talk about Bayesian deformation criterion or AIC or EIC, you pick the one that has the minimum. The model that is associated with the minimum is going to be the best.
Exactly.
Now, coming back to the R square, like you said, R square and the adjusted R square, those ones are the reverse of the case. If I have 95% of total variation in Y explained, that model is very good. But if I have like 40% of R square, that is very bad. So the criteria are there. You only need to be careful in choosing them. Thank you.
All right, sir. Thank you very much, sir. Sorry, please, can I ask a second question, sir?
Go ahead.
Yeah, why not?
Go
ahead.
All right, thank you very much. Sir, in splitting our model like to test and train, so do we have any rule of thumbs that we use for the percentage to use for the test and train? That's first one, sir. And the function that we use for the test and train, sir.
Yeah.
Do we have a single, a single code for like the one you use? I've seen some of the machine learning and other people that are doing this same of thing with different code. Is it advisable to to be used to a single code in splitting our test and train, sir?
Excellent question again. Thank you very much. Basically, you see that most machine learning facilitators want to train majority of the data. Can you hear me?
Right. Yes, sir.
And we believe the majority falls on the 70%. That's why it's 70% there. So, and then we can use, for me, I always want to train majority. And what I mean by majority is 70. Some can do 80, some can do 90, but in the spirit of fairness, I do 70-30. You could do 80-20 or 60-40, but you know, it's been found in some journals that 70-30 is quite very good now.
Wow. All right, sir.
All right.
Thank you very much. Thank you very much, sir, Doctor.
Appreciate.
I'm very, very grateful, sir.
Thank you. Thank you.
I really appreciate that presentation. I want to appreciate Ajia Bilkis Aderito. I didn't know you are into apps so much, Ajia Bilkis. That's nice. So you guys are the one championing.
Maybe it is you in Ibadan that are playing down our how Ibadan, that you are dividing our group. Are you
Okay,
not
no test, sir. So, yeah, my question is this. Dr. Folosha, I recognize you also. And Malam Abubakar. Thank you so much.
Thank you very much, sir.
Yeah, my question is this. I want Dr. Bishop to please shed more light on ML bench and carrots. I want you to shed more light on that because a lot of time people complain that they can't find data to even practice. I think many of us don't even know where those data are within our workspace environment. Thank you, sir.
Okay. Those data inside R is just a code. If I have cancer data in UI, I can say C.UI. It's just there's just summary name of saving the data set. You understand? So there is nothing in them other than variable name, object naming. You know what I want to advise everybody here is when you get the slide, go to her and invoke all the statements. Myself and my colleague, Mr. Olumide Oyalola, we have tried to check the data very well. Everything there and the codes are very good. Olumide, are you there? Hello? Is Olumide there? So the data, just invoke those codes with the data. You will see the data and everything. It's just a very good name. Any other question, please?
Questions?
Sir, thank you, sir. If I'm opportune to ask another question again.
Yes, hello. Good afternoon.
Help me. Yeah,
Yes,
hello.
Joel, can we have you?
My name is Joel Owuru.
Yes, Joel, can
my
we hear you?
question is
Yeah,
that
go on.
sometimes when you have sometimes you have in maybe quarterly or annual series,
Yes.
and you want to convert them to either monthly or weekly series.
Yes.
Then the process of converting them, I think some reviewers, they are not accepting conversion of that from one frequency to another. How do we do about it?
A very excellent question.
Hello,
too.
sir.
Yes, I'm here. Can you hear me? Can you hear me? Can you hear me?
Yes, sir. Yes, sir. Yes, I can
So,
hear you, sir.
Yes, what you
Yes,
just said now is common in time series modeling. Time series modeling. In time series modeling, we want to forecast using either weekly data or daily data or monthly data or yearly data. Of course, all of us know that each year contains 4 quarters. So, for instance, in a year now, January to March is the first quarter, and then March, April, May is the second quarter. January, February, March, April, May, June is the second quarter. July, August, September is third quarter. October, November, December is the fourth quarter. So if you have your data set that is broken down into daily, it's very easy to add them to get daily data. 7 days per week is very easy to make 4 weeks per month. So you can make that for monthly data. And of course, each year, a year contains 12 months. So there are packages in HAB that can convert them easily without any problem. I know of a package called Forecast. In that package, if you have weekly data or monthly data or daily data, you can bring them to yearly data with no problem at all. So one thing about REC, if you are looking for something and you have not found it, I can assure you that you have not searched very well. If you search very well, it's already done. Thank you. Any other question?
Yes, Ahmed Olaruwaju, you have been raising your hand. Ahmed, raising your hand. Ahmed, can you speak? Questions, please.
I've spoken. I forgot to lower my
Oh,
hand.
okay. Sorry. Sorry. Next question.
There is Fidelis also. One Fidelis is raising up his hand. Fidelis.
Okay, Fidelis. Fidelis, can we hear you?
Okay, allow Abubakar Ibrahim to talk if you want to talk.
No, sir. No,
Hello,
we
sir.
are waiting for more. Okay, yeah. All right. Fidelis,
Hello,
are you Fidelis? Yeah, please.
No, sir.
Question, please, Fidelis. We can hear you. Okay.
This is not Fidelix
Balogun.
Once again, I still have,
Okay, Balogun, please.
I have a
Go
question
on.
to ask again, sir. Sir, Doctor, sir, I want to clear my confusion about the logistic regression.
Okay.
Why do we name logistic regression a logistic regression? Do we call it dump name when we know that what logistic regression does is actually a classification? Then why the name logistic regression, sir?
Okay. I think, okay, you have spoken as somebody whose background is actually statistics. I will not be surprised if you have a first degree in statistics and so on and so forth. If you see that code if you see the slide I'm sending to you, you will see that
Yes,
I derived something and call it logit. And I was able to find
sir.
P over 1 minus P somewhere, which
Exactly,
is success and failure. So it is the name logistic comes from that logit link function, like as you rightly said the other time. So the name logit comes from the logistic because it's also a non-linear model. So the logistic thing we call it is because it's from it's just for the naming, because of the behavior of that link function. It doesn't do any harm to the model at all.
All right, sir. Thank you very much, sir, Doctor. Thank you, sir. Yes.
Yeah, welcome, Balogun. Thank you. Any more question? We can have 1 or 2 questions before we go. Two more questions before we wrap it up.
Yes, hello. Can you hear me?
Yeah, we can hear you. Robinson, go on, please.
Yes, Robinson. Thank you, Doctor, for the presentation. I've really learned a lot. My question goes back to the other formula you showed us at first, the linear model, where we had beta 1 and beta 2.
Yes.
One of the assumptions which were there is those parameters have to be don't have to be a square root or above. They have to have a degree less than 2, right?
Yeah, go ahead.
Yeah. The question I have is, how can I tell, because alpha and beta are constants and are just coefficients of the other variables. How do I tell that a certain parameter it has a degree more than 1 before even fitting the model, so that I make sure that I'm not fitting the wrong model? For example, even if the dependent variable is continuous, how do I make sure that now these parameters are a degree of 1 and not a square or above? Yes, that's my question.
Excellent one. And this excellent question will take me back. I want to go back to I want to take you guys all back to the slides. Can you see me? Can you see my slide?
Not yet, Doc.
Not yet.
You cannot see my slide. Can you see my slide now? Okay, I need to share. Host disable. Okay, can ask them to enable my screen, please. Host disable participant screen sharing. Let them enable my screen. I want to show something. To answer.
Hello, sir. Hello, sir. Yeah, you've been enabled.
Okay, I need to, because for me to answer Robinson's question.
Can share your screen now.
Thank you. I want to be able to, I want to show something. I'm back here. Look at this equation. Can you all see this equation? Robinson, are you here?
Yes, I'm here. I can see the see the equation.
This is alpha. I told you that it has a power of 1. And
Yes.
beta 1 also has a power of 1. And
Yes.
beta 2 also has a power of 1. This is a multiple linear regression, and we have 3 parameters in this model.
Just
The first parameter is what we call sigma square E, which is the variance of this error term. I remember I told you. Can you remember I said so?
Yes, I remember.
And now, because these are directly additive, if you look at this one, this x1 and this beta 1 have relationship, and this beta 1 is a parameter, is a coefficient of this x1. Beta 2 is also a parameter, it's also a coefficient of this x. So this beta 2 is quantifying this variable. Beta 1 here is also quantifying this one. So this is a linear model because they are linear in parameters, because the betas are easily they are additive easily. So it's very smooth. It's very smooth. You don't need to logarithmize this equation. You don't need to put a logarithm here or logarithm here to find an additive function. It's directly okay. Now,
Okay.
Let me go to the nonlinear model so that I can explain. Yes, for the nonlinear model, yes. Robinson, are you here?
Yes, I'm here, doctor.
Look at this gamma and the E function. Look at alpha plus beta xi. These parameters now are in powers. You know, they are like exponents of exponential function up there. This is not additive directly.
Okay.
Look at the denominator. You have the parameters inside an embedded exponential function. It's unfortunate I cannot write on this screen. If you take a logarithm of, as you are looking at this is a non-linear model. It is non-linear because it's not additive directly. And then the gamma is also a parameter, is now raised to power another parameter. Once you see functions like that, it is not linear. It's not linear parameter. So non-linear models are models that are non-linear in their parameter. This is just an example. So a way to linearize them is to take logarithm of both sides of this equation. If you do that, then you can find, it's a pity there's no time for that. Maybe next time we can ask Billy Keys to organize another one where I will go into nonlinear models and then you'll be able to see it more. So you may need to put logarithm into both sides of this equation before you can linearize. So it is the way the parameters be. Look at this second one also. This is beta. Look at the E function. There is another parameter on top of this exponential.
Hello.
They are not.
Hello.
So this is also a nonlinear equation. Have I answered your question?
Yes, thank you very much. I can see now the difference. Thank you.
All right. I'm here for any other question.
Yes. From Samuel. Hello.
Okay, Samuel and Nogwe. Go ahead, sir. Go ahead, sir.
Doc, when you were fitting the multiple linear regression,
yes,
you explained how to make variable selection via the stepwise regression.
Yes.
Then my question now is, for the logistic regression,
yes,
how can we make variable selection, supposing we have several explanatory variables?
That is a tough one there. For the logistic regression, when you have the several response variable, I know I will advise you do it one after the other. You first, if you have Y1, for instance, and then you have Y2, I will advise you take it one by one, because when you say you want to do that together, it's going to run with an extremely complex function that that will lead into a lot of parameters being estimated, and the problem of parsimony that we talk about to come up, where you have over parameterization. So it's better to do it one after the other.
Okay, using the same code.
Yes, you for instance, if you have two response variables, like you said, for me, I will do Y1 first of all, then I'll do Y2. I will only adjust the codes to identify which one I'm running at a particular time. When it's Y1 will be in the code. When it's Y2 will be in the code. Doing it together in that kind of stepwise situation will be very difficult.
Okay.
Hello,
Thank you,
sir.
sir.
Hello.
Yes, go ahead.
Hello.
Go ahead. Go ahead. Go
Hello,
ahead.
sir. Okay. Thank you very much for the presentation, sir. I really do enjoy it, sir. My question is on the linear regression. First of all, I would like you to, sir, shed more light on the multiple coefficient of determination and its adjusted version. Just the explanation. I know the calculation, but I really need the theoretical explanation behind the two, sir.
Okay. Yes. Let me first of all let's answer the first question. The first question is this linear model now.
Yes.
You can see that if I write y is equal to alpha plus beta 1 x1, if I did not include this part, Samuel, are you there? I mean,
no, this is Fidelis.
Fidelis. If this part, can you see my cursor?
Yes, sir, I can, sir. Yes, I can, sir.
If this part is not there, then this is a simple linear regression.
Yes, sir.
It is because I've got two explanatory variables, two independent variables that makes it a multiple regression.
Yes, sir.
So if this one is not there, the one my cursor is on. So if this one is not there, then we have a simple linear regression because there will be only one x1 and one y.
Yes, sir.
So, but the moment x2 and beta 2 comes in, it makes it a multiple regression because the x's are now more than one.
Yes, sir.
Is that okay?
Yes,
What's
sir.
your
Yes,
next
sir.
question? What's the other question?
Fidelis, sir, I said my question is that multiple coefficients of determination, that's r squared and adjusted r squared.
So for the r square and the adjusted r square,
yes, sir.
that r square, let's go to the result for you to see the r square. Now this is the r square, multiple r square. This one is 0.9934. Can you see it?
Yes, sir, I can, sir. I can, sir.
0.99 what?
34.
9934. And the adjusted is
0.9928.
Now, I said something that this multiple r squared is also what we call coefficient of multiple determination.
Yes, sir.
And when you say multiple determination, it means that you have y and x1 and x. You have 3 variables.
Yes, sir.
So what R square is measuring? R square is measuring the percentage of the total variation in my expenditure
dependent
that
variable
is being explained by my
independent variables,
my income and the other sources of income.
Yes, sir.
So my y, the total variation in my y that is explained by x1 and x2, like you said, the total variation in my response that is explained by independent variables x1 and x2. So so having done that, in this case it's 99.34. It's a very good regression, very good fit. So it means that the total variation in my expenditure is being explained by my salary and the other thing I put there. Now, the adjusted R square, it came from the idea of saying, okay, if the sample size is adjusted, if you have more sample size, if the data set is more than what we have, then the residual sum of square. When you have more data, then the residual sum of square is supposed to be smaller. So the adjusted R square is just a function that readjusts the existing R square, using the sample size So if you have done the theory before, you see a particular 1 over n minus 1, you just multiply that r square by that function, by that thing, and then you get 0.9928. So I just said that's why it's just a kind of improvement on r square. So because we believe the r square is spurious, and that r square can sometimes be misleading. So that's why the formula of r square is adjusted with the sample size, and that is what leads to the adjusted r square.
Okay, sir. Thank you very much, sir. Thank you very much, sir. Another question, sir, quickly, sir. I'm coming from the background of economics, sir. Yes, sir. Before we run regression analysis, they always tell us to carry out like pre-estimation tests, like unit truth test.
Okay.
Unit truth test, is it necessary for all time series analysis, or is just particular to our own field?
Those people in economics, for me, it's not always necessary, because if I'm doing anything time frame, you know, as an economist, all the financial data you have, they run over time, have you?
Yes, sir. Yes, sir.
For instance, now, just last week, the CBN sanctioned the board of First Bank, and unfortunately, First Bank is one of the most important banks in Nigeria. Over time, federal government has monitored First Bank revenue, income and expenditure. They are interested, even if it's another bank, the government may look the other way. Oh, this is First Bank. Is it not the most reliable bank people talk about in Nigeria? If you have the most reliable bank, where the board, the chairman of the board, also has taken a loan over time. You have taken a loan over time. It's like a thief that is being asked to run after policemen. So if a thief is asked to run after policemen, what do you think will happen? So you have a board, and you are the one in charge of, you are sitting on billions of dollars of money, both in Nigeria and abroad, and you yourself, you have taken a loan over time from the company, and you have not returned it. So you are waiting for the government to write your own loan off as bad debt, and then you want to be the one that is operating. So over time, most economic data, most macroeconomic or microeconomic data requires, they are collected over time, and that's why they become time series. So some data set requires the unit truth test, while some don't. What I always advise people to do is what we call exploratory data analysis, EDA. Once you have your data, plot them over time and see the behavior. In that case, you may not need to do any unit truth test. For time series data, there's what we call AR, autoregressive models. There's what we call the moving average models.
Yes.
And there is a combination called you combine autoregressive model with moving average, we call it ARIMA. We call that one autoregressive moving average. Then when you suspect there is an integration, you combine and say autoregressive integrated moving average, ARIMA. Later on, when it's seasonal, you say SARIMA, seasonal autoregressive integration moving average. So those things are developed. You might see me for details on that.
Okay, sir. Thank you very much, sir.
Okay, Doc, my second question.
Go ahead.
Let's say I have a data set on Y and maybe 4 independent variables, X1, X2, X3, and X4.
Yes.
How do I know when to fit a multiple linear regression model or non-linear?
Okay. That's a good question too. It depends on the situation. When you are looking for a relationship between income and expenditure, that one is usually very linear. When you want to build a model that is more complex, those ones are usually non-linear. For instance, this issue of COVID-19. This issue of COVID-19. I can give you an example to suit your case. Suppose AstraZeneca and what other pharmaceutical company? Suppose you have 4 pharmaceutical companies producing
Johnson.
Johnson. Suppose you have 4 different vaccines from four companies giving us vaccines. So I've heard that AstraZeneca vaccine, some people have taken it, and they started dosing off. Somebody took it, the person was dosing off at work. Some people took it and they had a serious issue. They brought it to me in an hospital. I rejected it. I don't want it. I said I don't want it. I say I'm not COVID-19, I don't have COVID-19. So that kind of a situation, the response to the application of each of the vaccines to human beings, that kind of situation can be very complex, because we have heard that that the COVID-19 situation was sponsored by some pharmaceutical companies, just so as to sell their vaccine. Now they are selling the vaccine. Some people are still saying it's a lie, that they are bringing in more COVID-19, or that they just want to sell the thing. So that kind of situation can be very complex. So, and in literature, very complex situations can be modeled as non-linear. And hardly can you find a linear situation today. Things are very difficult. Most things are not as they seem. Human beings are not as they seem again. There is an adage now that so things are not the way they seem. Not everything seems as it looks. So things are not normal anymore. Things are not linear again. So many situations are now very complex. How do you explain the COVID-19 situation that knocks out the whole world? It has never happened to us. We did not expect it. Look at so many angles that thing affected. It attacked so many things all over the world. Up till now, in the University of Ibadan, we asked them to allow our students to come back on physical class. They said no. They did not allow us. They said the COVID-19 has different variants, and that the thing is still around. So my answer to you, my straight answer is, how can you find a complex situation that can be modeled by linear models? And linear models are very scarce now, because so many systems and situations are very complex. Thank you.
Okay, Doc, thank you very much.
So, Doc,
What I was trying to find out is this: if we have data sets, is there not a way, data sets of this kind I mentioned, is there not a way of justifying that the relationship between Y and those 4 variables are not actually linear before moving?
I already answered that now. In the previous question, I said exploratory data analysis. Exploratory data analysis. Once you have your data, and you plot X against Y, you plot Y against S, and you have a kind of straight line. If you have a kind of straight line in such a way that you can find a line of best fit, where majority of the line will fall on that line, that one is suggesting linear model. That one is suggesting linear relationship. But if you have a curve, like a demand and supply curve in economics, that is curved, that is not straight line, any curve that is not a straight line, that one is suggesting non-linear model. That's a great question.
So among the 4 variables, supposing we have, say, Y, X1 exhibiting linear relationship, maybe X2 and Y exhibiting linear relationship, and one of the variables or 2 does not exhibit, what can we do?
Yes, if I were you, I will model those that have linear variables separately. I will pick, for instance, I'll pick Y and X1 linear, Y and X2 linear, Y and X3 linear. I will fit linear models to them. The one that is not linear, I will do Y and X4 non-linear, and I will write reports on each of them.
Okay, thank you very much. I'm grateful.
Yeah.
Last question, please, sir. Doctor?
Yeah, last question.
Go ahead.
All right. Thank you very much, sir. Sir, I noticed that in our codes and the results we are getting from the data we taken from R default. I noticed that our R square is always perfect. As in,
it's almost
like
perfect.
We have
okay.
It's almost perfect. Like we have a 99 or 96%. And some of example we see online in our online tutorial and the likes, that is how it always be. But in real life situation, it is not always like that. So I want to know if those data in R, like the examples data that we were given in R to train ourselves, are those data being, as in, are they clear, as in mostly clear to the extent that when you fit the model, you have a perfect or like close to perfect this thing, unlike the real life situation whereby you gather data from here and there, and you want to be fitting and tuning, still clear, and do all those sort of sort of data engineering and the likes that we used to do for the data. But why is it so? Since they want us to, is it that those data in R are perfect, so we should not even bother ourselves making it as a kind of something that we can rely on, that okay, if I'm able to fix this up, yes, I'm good to go for a real life situation. So my second question, sir, let me ask the two together, sir, so you can help me answer the two together, sir. I'm sorry for the too much question.
No worries, no worries. Go ahead, go ahead.
Thank you very much, sir. The second thing is, when we're doing the logistic regression modeling, I noticed that you did not include domain variable function to actually create the domain variable for the categorical data, the response variable in logistic regression. And I noticed that some of those people, some of the tutorial we've been seeing out there, they will create a domain variable of maybe yes or no that we actually want to model. So I want to ask if there is no penalty for that if I'm not doing the domain variable as time goes on in my sojourn.
Yes, very, very good questions. Let me start from your second question.
Thank you, sir.
You know, I told you that there's a lot of theory that is involved in the logistic regression that I omitted. For instance, for you to estimate the parameters in theory, you have to do some iterations. I removed those ones. I do not want to bombard our site with so much equation. That was why I removed the domain variable. So it's of no harm. But because of the kind of audience I had in mind that I was talking to, that was why I removed some of those things, so that those guys. On the second question, the R squared being perfect. Well, let me quickly take you back to the data we created. Look at this data. You can see that we generated the data ourselves. Sequence 1 to 10.
Yes.
Random number, uniform, 25. In fact,
37. Yes.
In fact, random number 35. If you after you receive this slide, if you try the random number, this one, and do it on your, it will be different from the one I have that I've run here, because it's randomly simulated. So
yes, sir.
You will, although the R square is likely going to be very close to mine actually. So if you run it again, the values you find on the slide will be slightly different. Okay,
sir.
So these are just hypothetical values that are generated by me. My equation to get data was just written by myself. And the fact that it's 99% is just by providence, it's just by incidence, just by coincidence. It could be 92, it could be 91, it could be 90, whatever. Okay. So to answer that question directly, it doesn't have to be 100%. But when you have 99%, you want to be skeptical that, oh, is the data falsified? Well, I can agree with you that, this data is not from a clear experiment. If it has been from a clear experiment, you don't want to, you may not get something close to 99%.
Okay,
Thank you very much.
Sir, one last question, sir, before I go, sir.
Okay.
Before you go. Sir, then when do we have the problem of overfitting?
Yeah.
Is it is it possible we have more than 100% when we are fitting? Or when do we say we have the problem of overfitting when we are fitting our model, sir?
Yes. I said something about parameterization the last time, or what we call parsimony. That parsimony has to do with you having several variables in that system. Like you were talking about X1 to X4 now. If I have X1 to X1 million, that would be an overfitting case, because you will have several parameters. And of course, what we call overparameterization will set in, and result will be complex to interpret. And of course, you have residual sum of square will be very high. Standard error will be very high. And those models are not, we don't encourage those models. And that's why we say, okay, once you have 1 million explanatory variables, gentlemen, can you fit them gradually, maybe in 2s or 3s? Don't fit 1 million variables at the same time. So when you fit so much variables, you expect so many parameters, in that case, you have overfitted your model. So it's grossly discouraged in statistical modeling.
Thank you very much, Doctor.
Yes. I can
Yes,
hear
we
you.
can hear you now.
Yeah, so I think we have come to the end of this session. But before I hand over to Bill Keys, I would like to announce our next webinar, which is titled Interactive Dashboard Using R Shiny Dashboard, by our own Bill Keys, Wumi Aderinton. Date is June 12, 2021, and venue is online. So we expect to see more people. We appreciate everybody who signed up. Bill Keys, over to you.
Prof, I'm really overwhelmed with what the Prof has done, and I really look forward to getting you on board again, because you're a teacher. You are a teacher, and you've really demonstrated that today. And I'm speaking on behalf of everybody that we really had a nice time today. So
Thank you very much.
so grateful. I'm so grateful, and I'm so grateful. So we're looking forward to, no matter what, I will always drag you here. I would always bring you on board, no matter what. So always, always, no matter what, I know you will deliver. So I would really love to have you next time. So I'm grateful to everybody. So I want to show our really sincere appreciation to all those who attended the program today. I actually want to appreciate the University of Ibadan R user group, as well as the Ibadan R user group, and everybody from around the world who joined us today. So I want to acknowledge the presence of Jason. I really appreciate your presence here. We appreciate your support always. So on this note, I want you to please look forward to our next webinar, and we look forward to seeing you. Thank you so much. Thank you.